Hello, my name is Kyujin Sim,
Hi, my name is Muhammad Ali Sharin Aljari and we're from group 35.
35, and we're going to explain the four components each.
And we're going to summarize how data is transferred throughout our MIPS, and we are going to show it working on our FPGA machine.
Thank you. Hello, this is Chris, and I'm going to explain the control unit. As a summary, the control unit is responsible for setting all the control signals so that each instruction is executed properly. It decodes instruction to determine what segments will be active in the data path. It generates signal to set marks to correct input, operation code to ALU, read and write register file, and memory for loading and storing, update of program counter, which is responsible for branches, and its target address computation. Our control unit is made of two parts, ALU decoder and main decoder. Firstly, ALU decoder specifies what operation ALU performs. For example, 000 indicates AND function, and 001 indicates OR function. In ALU control, which is the output of the ALU decoder, basically, it is based on operation code and functional field. Lastly, main decoder uses fields from instruction to generate control. We connected the fields of instruction to the data path via the main decoder. Anyway, most of the signals can be generated from the instruction opcode alone, and not the entire 32-bit word. It tells the data path what to do, based on the instruction that currently being executed. Thank you.
Hi, I'm Muhammad Ali again. I'm going to explain more on ALU, which we also use in our single cycle processor. So, ALU is an arithmetical logical unit that combines a variety of mathematical and logical operations into a single unit. And ALU is capable of computing, as I said, a variety of mathematical and logical functions, such as operations needed for MIPS core instruction set, which are add, subtract, and or zero test, comparison. You get the idea. The general strategy. Different circuits combined by multiplexer select becomes function select for ALU. Inverting B input for subtraction, feed output of high order bit of adder to low order bit for set on last operation, use OR gate on ALU output for equal test. So what I explained just now is basically how the ALU operates. So if we scroll down here, we can see that there is a switch for the ALU, of which it is labeled F, which is the function switch. Alright, this here has 2 bits. It's carried 2 bits of data, and here it carries another bit of data, of which it is connected to the select switch of multiplexers. So when all of the function switch are zeros, the output will be the A and B, the product of the input value of A and B. 111 will result in set if less than, that will give output 1 when input A is less than input B. Otherwise, the output will be 0.
Hello, this is Hyujin Sim again, and I'm going to explain one of the most important components in our circuit, the register file. A register file is a small set of high-speed storage cells inside the control processing unit, which is widely known as CPU. It includes 32-bit general-purpose registers, which stores operands of instructions such as add, sub. However, these files makes possible to simultaneously read from 2 registers and write into 1 register, as it is appropriate for MIPS processor.
Hello, I'm Muhammad Haziq, and Today I'm going to explain on multiplexer, specifically 32-bits multiplexer. In our single cycle processor, we are using 4 32-bits multiplexer, which I'm showing here right now on the screen. Alright, but the basis of it is a single bit multiplexer. Basically, multiplexer chooses an output among several possible inputs based on the value of a select signal. It selects between one of n inputs to connect to an output. It is built using two levels of logic, which comprises of two AND gates, one NOT gate, and the output is combined by using an OR gate. It can also be built from tri-state buffers. It is arranged such that exactly one tri-state buffer is active at all times. However, we will form a 4-bit multiplexer by arranging 1-bit multiplexer in such way that we connect it to a bus. And the 32-bit multiplexer is connected in such a way that the 4-bit multiplexers are arranged so that it can carry 32 bits of data through it.
Hello, this is Kyujin Sim, and I'm going to explain the clock. Clock is a square wave that is 50% duty cycle wave, and it can be either 0 or 1. It determines how fast my design can run. We are going to use an adder with a register file, an array of flip-flops, to implement a counter that increases the number by 1 when the rising edge of the clock arrives, which this can be checked by using the waveform. The counter increases by 1 whenever the rising edge of clock, CLK arrives. It also resets its output to 0 when it reaches the constant number defined in the constant block.
Hello, right now I'm going to explain more on register, particularly 32-bit register, which we will use in our single cycle processor. Registers are made using positive edge triggered D flip-flops, which I'm showing here, which circuit is in this image right now. However, D flip-flop is made up of D latch, which itself is made up of an SR latch. Right. You can see here when I'm showing you here the circuit. Now let's go back to D flip-flop. Alright, D flip-flops is active when there is clock rise from 0 to 1. When there is clock rise from 0 to 1, data D will pass through Q, of which the first D latch will be transparent. If it is otherwise, the output Q will possess its old values. This acts as memory, as it holds the value if there is no clock rise. And there is another variant of flip-flop, which is resettable D flip-flop, of which we put a not reset button with the not reset input with the data input and combine it using an AND gate, and its product is an input for the D flip-flop. Basically, a resettable D latch, a resettable D flip-flop. When the reset button is equals to 1, of which in this case not reset will be equals to 0, Q will be forced to have the value of 0. If otherwise, when the reset button is 0, the flip-flop behaves like an ordinary D flip-flop. Alright, by using resettable D flip-flops or D flip-flops, we can form 4-bit register by connecting them to a bus. This allows them to process 4 bits of data, and from this 4 bit register, we can create a 32-bit register, which consequentially process 32 bits of data.
Hello, this is Gyujin Sim, and I'm going to explain the ROM. The ROM component can load and display MIPS assembly language, which helps with debugging and saves me from having to write test programs in machine language. I set the $sign T1 and T2, T3, T4 as a square number, current number, loop count, and total respectively, and initialized by 0. Then my loop statement. I use back statement, which means jump to given address, if 0 flag is set. Then count my loop count and the total number of current numbers. Then I made the increasing statement. I store the location of square number and go back to J loop. So basically, after number 1, find the square number of 2 and 3, so on, so that the number should be shown as 1, 4, and 9, so on. After writing all of the code, run it and go to assemble to check the location of the code, and I copied the machine language into ROM file in the MIPS. Then we made as a block.
Hi, I'm Muhammad Alik again. Now I'm going to explain more on left shift to places, which is another component in our single cycle processor. So first I'm going to explain about what is shift left logic. Shift left is where one position of each bit moves to the left by 1. The low order bit or the rightmost bit is replaced by a 0 bit, and the high order bit, which is the leftmost bit, is discarded. Now, this is left shift 2 places. This is not 1 places. So, for 2 places, for left shift 2 places, it is just the same concept, but it shifts by 2 positions. Shifting by 2 positions is the same as performing a 1 position shift 2 times. Shifting by 0 positions leaves the pattern unchanged. Shifting an n-bit pattern left by n or more positions changes all of the bits to 0. There are, for example, an original pattern which has 1 0 1 0 0 1 1 1 will result in a one left shift in 0 1 0 0 1 1 1 0. However, if it is left shift 2 places, it will result in 1 0 0 1 1 1 0 0. Hi, now to summarize everything using all of the components that we have explained earlier. The data is transferred through all of the components and is displayed through the display driver. Now in this circuit, we use the example code given, which is the instructions are in the ROM file, and we will show you how it works on the machine. Alright, here is how our program counter will work. It will count from 0 to 9, and after 9 it goes back to 0.
Hello, this is Gyujin Sim, and I'm going to explain the ROM code which I wrote. So basically, if you can see the screen, I used the add I function, which is add immediate. That means add a register and assign extended immediate value and stores the result in a register. So as you can see, I set T1 as square numbers, T2 current number, T3 loop count, T4 as the total. And after that, I move on to the loop statement, and I will say use the back statement, which is branch on equal. That means branches if the 2 registers are equal. Then I use the add statement, which means basically add. It means adds two registers and stores the result in a register. So that means, for example, the line which I use adds T4, T4, T2. That means the adding the current number to the total. So after that one, we're moving to increasing statement, which I made. Then I use the SW statement, which stands for store word. That means the contents of $T is stored at the specified address, which is 0xFFFFFFF0 means returning on, and oppositely 1 is turned off. And lastly, which I use the J loop. That means jump. J means jump. It means jumps to the calculated address. And after writing this old code, I click the run and assemble, which we can collect the location of the source and code. Then we copy this into this ROM file. And as we change the location and the code, we have to change the array because there's 14 lines, so 0 to 13. So this is how our square numbers works. And when we use the reset button, it goes back to the initial one, as you can see.
Thank you, Group 35.